Okay, now let's think about what you've learned most recently. You've been learning about series, and a series is a sum of an infinite number of terms of a sequence. And we are interested if the series converges or diverges. And you know, it's an interesting academic exercise, but where would it be, you know, why would this be used? And like, how could this be used in a real life problem? Okay. Well, one thing that like this knowledge you've learned so far in chapter 8 is applicable towards what's called an interval of convergence for a power series. Now, what's a power series? All right, let me show you. Okay. Power series is a series of this form. You have the summation where n equals 0 to infinity of where the terms of your series are given by coefficients c sub n times x to the nth power. Okay, these c sub n's are called your coefficients. They're the coefficients of the series. And for every fixed value of x, okay, this is important. For every fixed value of x, the series will generate a series of constants that we can test for convergence or divergence. So the series that you've had so far in like sections 8.2, 8.3, and 8.4 didn't, I mean, for the most part, they did not involve an x. Okay. I mean, you did look at some in section 8.2, some geometric series that where the radius of convergence involved a function of x, like a cosine of x or x plus 2. How many recall that? How many recall that in their homework, seeing that? Okay, Jacob remembers it, and Nicole remembers it. Well, okay, so you've seen a little bit of this, but what we're doing now is we're focusing on these power series. And the idea is that you're going to learn that you can actually take functions like the sine of x, the cosine of x, e to the x, the log of 1 plus x. You can take functions and write them as power series. And it's an absolutely amazing idea that we can take a function and express it as a power series of the form that you see here. But the function will only be equivalent to its power series over what's called an interval of convergence. Okay, so it's not necessarily the case always that the function will equal its power series for all values of x, for instance. Because a power series, okay, may converge for some values of x and diverge for other values of x. And what they do here is they mention here that this, and let me just highlight a little bit here. They've actually are reiterating what I just mentioned. The sum of a series is a function. Okay, you can write that power series as a function whose domain is the set of all x values for which the series converges. And notice that this function f would resemble a polynomial. Okay, and we like polynomials because they're easy to work with. So let's look at an example here of a power series. Let's look at a simple example. Okay, look at this series here. the series where n equals 0 to infinity of x to the nth power. If we enumerate that power series, the terms are going to be 1 plus x squared plus x cubed plus x to the fourth, and so forth. Okay, right? Well, what does that series resemble? That series that I've enlarged. I mean, what's that series remind you of? That's right, Renat. It's a geometric series. Oh, well, what's the common ratio? If it's a geometric series, what's the common ratio? It is x. It is x. Because one, like if you take the second term x and divide it by the first term 1, you get x. If you take the third term of the series, x squared, which is x squared, and divide it by the second term of the series, which is x squared divided by x is x. And this continues. So there's a common ratio of x, and we know that the common ratio, that a geometric series will converge if the absolute value of its common ratio is less than 1. And therefore, our power series converges, this particular power series, I'd like to try to just highlight it. Let me see if I can. Yeah, this particular power series will converge when x is between -1 and 1, and diverge when the absolute value of x is greater than or equal to 1. Okay. So, and they say see equation 8.2.5. When they're referring to that equation, they're just referring to the section 8.2. Let me see here. One moment. They're referring, let me see, what are they referring to? Hold on. Yeah, they're referring actually to example 5. This relates to example 5 actually in section 8.2. And there's equation 8.2.5 there. But this is an example, an easy example of a power series, and it turns out it's a geometric series. Now there are other very famous series, okay, like for instance a trigonometric series. That's a famous power series, okay, a trigonometric series. How many have heard of Fourier series? How many maybe have heard of a Fourier series? It might be a little, okay, Jacob's heard of it. And you know, there's different, like when you take different courses in the future, these power series are going to come up. So what we're focusing on is for what values of x would a power series converge, for what values of x would a power series diverge. Okay, so let's look at a simple example, and then I got some that we'll look at too. Okay, but let's look at. Oh, by the way, just another comment here. So you can have, if you want to be very general in terms of what a power series is, you, instead of x to the nth power, you know, you have the series n equals 0 to infinity with coefficient c sub n, and then you know, you have x minus a to the nth power. So before you had x to the nth power, but you could make that x minus a to the nth power, and then that's very general, because like a could equal 0, which would give you the power series that you just saw before. But if you use this form of a power series, it's called a power series, in x minus a, or a power series centered at a. Okay, and naturally the first term is c sub 0, and that's because x minus 0 to the 0th power is equal to 1. Okay, so they're going to adopt that convention. Are there any questions on this so far? Okay. Okay. Well then let's look at just this first example. Okay, and I have a lot of things highlighted here. Let me try to remove them here. So hold on. So they ask for what values of x is this power series convergent? So the terms of the series are n factorial times x to the nth power. Now, let me ask you, what the terms of this series, what does n factorial do as n increases? What does n factorial do? Does it grow or get, I mean, what does it do? It grows. That's right. That's right, Renato. So like 0 factorial equals 1. 1 factorial equals 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 3. So it looks like the terms of this series might be growing, okay, for any value of x you use. Got to be a little careful about that. We're going to determine convergence of this series, power series, using the ratio test. How many remember the ratio test? You just learned that from section 8.4. Okay, good. Incidentally, how many used the ratio test and tried to use it and got an inconclusive result? Because when you did the ratio test, the limit was equal to 1. All right, so Jacob had that experience. Paul had that experience. So you have to be careful with the ratio test. It's kind of, students love to use it, but it's really, I mean, it's best used in complicated series like this one here. So okay. The nth term of the series is n factorial times x to the nth power, and here now we are applying the ratio test. And n plus 1 factorial divided by n factorial is just n plus 1. Okay, let me just show you that little step there so that maybe I'll go to the whiteboard. One moment. Hold on, class. So we're looking at example 1 here. Okay, so let me ask you. 3 factorial over 2 factorial. 3 factorial is 1 times 2 times 3. 2 factorial is 1 times 2. That gets you 3. What do you think 4 factorial over 3 factorial equals? That's right. It equals 4, because 4 factorial is 1 times 2 times 3 times 4, and 3 factorial is 1 times 2 times 3, and you get 4. Okay, now we could keep going. What do you think n plus 1 factorial over n would be, over n factorial would equal? Based on, you know, these two. Yeah, that's right, Leping, n plus 1. But if you wanted to be, you know, if you wanted to write it out, well, first of all, n factorial is 1 times 2 times 3 times 4 times, and you keep going all the way to n. N plus 1 factorial is 1 times 2 times 3 times 4 times, and you keep going to n, and then n plus 1. So all of the terms are going to simplify out, okay, and you're going to be left with n plus 1. And this is why n plus 1 factorial is equal to n plus 1. Okay? So now let's go back to the example then that we were looking at. So okay, so what happens is then, applying the ratio test to this series, the limit of the ratio, or the limit of the absolute value of the ratio of the n plus first term to the nth term, will equal the limit as n goes to infinity of n plus 1 times the absolute value of x. So the x could be positive or negative. So we need to keep the absolute value there. And you know, x to the n plus first divided by x to the nth power is x to the first power. That's why we get the absolute value of x. Now, as n goes to infinity, that's going to equal infinity. And this means then, by the ratio test, this particular series diverges anytime x is not equal to 0. In other words, the series only converges when x equals 0. And by the way, if x equals 0, what's the value? What would the series equal if x were equal to 0? What would the power series equal? That's right, Renaud. It would equal 0. If we were to substitute in 0 for x, for that power series, all the terms would equal 0, right? Because 0 to any power would be 0. So there you go. There you go. All right. Are there any, who's feeling good about that? Okay, let me see. Nicole's feeling good. Just adjust my thing here. Who else here? Forgive me. Tal's feeling good. Renaud's feeling good. Okay. Are there any questions? Okay, well then let's go ahead and get to a few examples. The book has nice examples, but I want to do a few of my examples too. So by the way, So the interval of convergence for this example is just the value 0. All right. Let's go ahead here. Let me give you a moment to copy this example down. Okay. Okay, so what we want to do here is find what we call a radius of convergence and an interval of convergence of the power series. This power series. Power series where the terms of the series are given by -1 to the nth power times n squared times x to the nth power divided by 2 to the nth power. Really the most important thing is the interval of convergence, because the interval of convergence tells you the x values for which this power series would converge. Okay, so let's go ahead and look at the solution here. What I want to do is, first of all, talk about what the power series looks like. I want to write some terms of the power series out. So I do this on the next page. Okay, what does this power series look like? Now again, this is not exactly part of the problem, but I think it's, I think it's helpful. Anytime I can make things less abstract for you, I think it's good. So what's this power series look like? Well, okay, let's write some terms of the power series out. The index starts at what? What does the index for the power series start at? What's your starting value for n? N equals 1. That's right. So the first term of the series is when n equals 1, right? And then I guess the second term of the series would be the term when n equals what? N equals 2. Okay, good. And then n equals 3 would give us the third term of the series. So we're just enumerating the terms of the series out. And then, I simplify those terms to get me then, well, the first 3 terms of the series. Okay. How many find it helpful just to see that at least once? See some of the terms. How many is it helping you feel a little more like understanding? Okay, good, Jacob. Good. And thank you, that other person. I have to check my little people button here to see who replies. Okay, so what test are we going to use for this particular power series to help us determine the interval of convergence? What test again are we going to use? That's right, Nicole. We're going to use the ratio test. Absolutely. Absolutely. Okay, so we will let then in the ratio test this -1 to the nth power times n squared times x to the nth power over 2 to the nth power. That's going to be our a to the nth power, right? That's going to be our a to the nth power. I'm sorry, that's going to be our a sub n in the ratio test. So let's go to the next page. All right, so a sub n is -1 to the nth power times n squared times x to the nth power over 2 to the nth power. And now I'm applying the ratio test. So the n plus first term, so the nth term, okay, that's easy enough to see there in the denominator. Okay, the n plus first term, I just get that by substituting n plus 1 everywhere n goes. Okay, so in the term, wherever there's an n, I substituted n plus 1, and that'll get me the n plus first term. But what happens here is that I have a fraction divided by a fraction, right? I have a fraction divided by a fraction. And you learned probably way back in maybe even elementary school or middle school, if you have a fraction divided by a fraction, you multiply by the reciprocal of the bottom fraction. And so that's what I'm doing here. This here, 2 to the nth power over negative 1 to the nth power times n squared times x to the nth power, that's the reciprocal of the denominator. And I'm going to be very structured about this. I'm going to group like terms then, or in my next step, I'm going to group like terms over each other. So this is the kind of work I would want to see, for instance, on the final exam. This will be material on the final exam, section 8.5. And this is, you know, this is the good work, right? Okay, and negative 1 to the n plus first power over negative 1 to the nth power is negative 1 to the first. Okay, and then n plus 1 squared over n squared is just n plus 1 over n squared. 2 to the nth power divided by 2 to the n plus first power is just 1 over 2 to the first power. And then finally, x to the n plus first power divided by x to the nth is equal to x to the first. How many found it helpful when they did the ratio test in section 8.4 to group like terms together, like I'm doing here? How many found that to be helpful? Good. Renaud found it helpful. All right. And Tal found it helpful. Good. Good. All right. Are there any questions before I go to the next page? We're not done yet. We got to take the limit. We got to take the limit of the absolute value of this expression. What's going to happen, by the way, to the negative 1 power? What's going to happen to negative 1 to the first power? What's that become? Because we're taking an absolute value. That's going to become a positive 1. So that kind of goes away, right? All right, and so now the limit as n goes to infinity of the n plus first term over the nth term is going to be equal to the limit of as n goes to infinity of the absolute value of n plus 1 over n squared times x over 2. But the n plus 1 over n squared is positive, so we can bring that out in front of the absolute value, right? You can bring that out front. And so we're left with the limit as n goes to infinity of n plus 1 over n squared times the absolute value of x over 2. You see, x could be negative, right? So you can't bring the variable. I got to be careful here, unless you had like an x squared or something where no matter what x is, the variable portion is always positive. The function of the variable is always positive. Unless you have that, you have to keep that absolute value there. And so the limit is going to equal the absolute value of x over 2. That is going to be our L in the ratio test. That will eventually be the common ratio for the terms of this power series as n gets large. The power series is going to behave like a geometric series with common ratio x over 2 as you move out into the power series and study the terms. So therefore, by the ratio test, our power series is going to converge when the absolute value of x over 2 is less than 1. Well, what that would mean, Renat, is if the absolute value of x over 2 is less than 1, that means the absolute value of x over 2 is less than 1, because you know the absolute value of a fraction is the fraction of the absolute values, and so yes, absolute value of x would be less than 2. Absolutely. Okay. Are there any questions? All right. Well, so when we say the absolute value of x over 2 is less than 1, that means then that, well, think of it like this. We don't want so there are really two ways to do this, okay? If you, I mean, let's just take an analogy here. If you had, like, this is just separate now. If you had the absolute value of a is less than 3, what can you tell me about a? If the absolute value of a is less than 3, what values would a be between?
3 and -3.
That's right, Maria. Very good. Okay, well now let me I'm just doing a separation here. Let's say you had the absolute value of an apple, and that were less than 3. What's that going to tell you about the apple? What would the apple have to be between?
-3 and 3.
That's right. Now, why do I do that with the apple? Well, I think of this x over 2 as like my apple. And if the absolute value of x over 2 is less than 1, then x over 2 has to be between -1 and 1. And then if we multiply through the inequality by 2, which won't, well, if we multiply through this inequality by 2, which won't change the inequality signs, won't switch them because 2 is positive, that means x is between -2 and 2. And so this means our power series converges when x is between -2 and 2. And it will diverge. It'll diverge if x is greater than 2 or x is less than -2, because that would cause the common ratio, that would make the common ratio, or the absolute value of the common ratio, greater than 1. So if x is greater than 2 or x is less than -2, our power series will diverge. So you see what happened here is we're getting an interval. We're getting an interval of convergence. Our power series will converge when x is between -2 and 2. In other words, the power series is good for those values of x. But we can ask ourselves, are there any more x values where our power series would converge? Do we have all the x values? What about when x equals 2 or -2? What about when the common ratio is equal to 1? Well, when the absolute value of the common ratio equals 1, that would happen when x is -2 or +2, but the ratio test gives no information in those cases. So you see, what we're doing is we're trying to look at the entire x interval, the entire number line of x's, all the x values from -infinity to infinity, and pick out the x values over which this power series converges. Well, the power series we know converges when x is between -2 and 2, and the power series would diverge if x is greater than 2 or x is less than -2. But what about when x equals plus or minus 2? Well, we can't use the ratio test to help us there, because the ratio test is going to give us, in the limit, a common ratio of 1. And when absolute value of x over 2 equals 1, that would happen when x equals -2 or +2. So those two values of x, I can't use the ratio test to establish convergence or divergence at those particular x values, because the ratio test gives no information. How many remember that? That when the ratio test, when the limit equals 1, the ratio test is uninformative. Okay, Nicole remembers that. Jacob remembers that. That's from section 8.4. Tall and all right. So, but that doesn't mean we just walk away. We just walk away here. We don't just walk away. We have to test if x equals -2, if the power series converges at x equals -2. We have to test if the power series converges at x equals +2. And the only way we can do that, class, is by manually checking the power series at those values. Okay, let me give you a moment here. Okay, are there any questions before we move on? Okay. Okay, well, let's go ahead then and test these values out. Let me show you how this works. So at x equals -2, I'm going to plug that into the power series. Remember what our power series is. Our power series is the sum where n goes from 1 to infinity of -1 to the nth power times n squared times x to the nth power over 2 to the nth. That's our power series. So I'm going to plug for x here, I'm going to plug in x equals -2. And then I'm going to simplify, this is an equals here, I'm going to simplify the power series. Well, the power series now is just a regular series because we substituted in a value of x. So this is now like the series that you've been seeing from sections 8.2, 8.3, and 8.4. Okay, so the power series will reduce to the sum where n equals 1, at x equals -2, the power series will become the series where n equals 1 to infinity of n squared times 2 to the nth power over 2 to the nth power. But that just equals then the series whose terms are n squared. Well, that series has to diverge, right? Because 1 squared plus 2 squared plus 3 squared plus 4 squared and so forth. The terms are not getting smaller. So there's no chance that this series converges. Now remember, just because in a series the terms get smaller and smaller, just because if the terms approach 0, that's not enough to say that the series will converge. But we definitely know that for the series to be able to converge, the terms have to approach 0. That's just to give it a chance of converging. It doesn't mean the series will converge, but we know if the terms of the series aren't approaching 0, definitely the series will diverge by the test for divergence. Okay, now are there any questions on that? All right, well then let's try x equals 2. Let's substitute in the power series x equals 2. So I want to say this means, by the way, this result above here means that the series will diverge when x equals -2. Now when x equals +2, we plug 2 in for x in the series, and we end up getting this oscillating series. And I write out some terms of the series, okay, just to help me intuitively feel comfortable with the series. And I can see, yeah, these terms aren't getting smaller. This series diverges also. So at x equals 2, the power series diverges. Please let me know if you have any questions. There's no bad question here, right? Okay, so you see, you can see how what you learned earlier in chapter is tying in to section 8.5. It comes in because when you test the endpoints of, for convergence or divergence. Okay. So then, and this kind of work, incidentally, would be expected on for the final exam. Sometimes students sort of, they gloss over this kind of work, where they test the endpoints, but it needs to be there, in your work. So please train yourself to show this kind of work. Okay, well then, what is my interval of convergence? What is my interval of convergence? Okay, I'm going to write down four answers here, and you tell me which one is right. Okay, so here's choice 1. Here's choice 2. Okay, so sometimes the endpoints, the series will converge at the endpoint. So, but I'm not saying it didn't for this series, but I'm just writing down the possibilities, all the possibilities, but I mean only one of them's right, right? Closed endpoint, open endpoint. Okay, so choices 1, 2, 3, and 4. What's the right choice for the interval of convergence? Okay, good Maria, good Lepine, good Renaud. It's going to be the first choice. That's your interval of convergence. So let's go to the next page. Here we go. The interval of convergence for our power series is the open interval from -2 to 2, which I've drawn here. Here's the x-axis, and there's my interval. Now, associated with an interval of convergence is what they call a radius of convergence. If you take your interval and split it in half, the length of one of the halves is your radius of convergence.
So why didn't we have to test anything, say, greater than 2 or less than -2?
The reason is, I'll show you why. I'll go back here, but let's, one moment, Nathan. All right, I'll go back in. Does everybody have this page copied okay? Maybe give me a thumbs up if you're good. Okay, Nicole's good, and Tal's good, and wonderful, wonderful. Gloria's good. Yeah, all right. Okay, so if I go back here, to when if I go back here, well, no, hold on, I got to go back further. Yeah, so we agree that when the absolute value of the common ratio is less than 1, the power series converges for those values of x, right? Well,
I understand now.
right. When would the ratio test says then that the power series would diverge when the absolute value of x over 2 is greater than 1, right? And so it's a good question, Nathan, good question. And so if I go to the whiteboard here, hold on here, absolute value of x over 2 greater than 1 means the absolute value of x over 2 is greater than 1, which means the absolute value of x is greater than 2. Well, you know, when is the absolute value of x greater than 2? That would be for values of x larger than 2 and values of x smaller than -2. So this means then that x would be greater than 2 or x would be less than -2. So you see those, that would be where we have divergence. You see, so all we need to do when x was between 2 and -2 by the ratio test, we had convergence of the power series. The power series converged for those values of x. So if we you know, consider this information and this information, all that's left is what happens at x equals -2 and what happens to the power series when x equals +2. Does the power series converge for those x values? And but we have to test them independently. All right. Okay, good question, and you're welcome. You're welcome. And so, therefore, hold on here. Therefore, there's our answer. Okay, let's do another one. Let's do another example. I'm gonna stop the recording here and make a new recording for the next example.